My name is Chuanpu Fu from Tsinghua University. Today I'm going to introduce our new research article. In this work, we address a problem in the scope of network security and machine learning for security: how to capture encrypted malicious traffic. Our solution utilizes the interaction patterns among users and attackers, and the interactions are represented by a specialized graph. By learning the features of the graph, our method can detect various attacks with high accuracy, high efficiency, and low consumption. Okay, let's move to the details of this work. Nowadays, traffic on the internet has been widely encrypted to protect its confidentiality and privacy. It is reported that over 94% of Google web traffic is encrypted. Similarly, over nearly 80% web pages loaded by Firefox browser enables HTTPS, and over 98% website listed in Alexa Top 1000 enables HTTPS. The growth is unprecedentedly rapid compared with the ratio reported in 2014, only around 3.8%. Currently, more and more users benefit from deploying traffic encryption protocols, which forbid eavesdropping, tampering, and auditing. But unfortunately, traffic encryption is double-edged. Attackers can also abuse the traffic encryption to conceal their malicious behaviors. For example, data breach, exfiltration, and malware delivery. A white book published by Cisco revealed that at most 70% attacks were constructed by encrypted malicious traffic, and the corresponding financial loss had been predicted above $3 million. As a result, by encrypting attack traffic, attackers can easily evade existing traffic detection systems, which aims to identify ongoing attacks by inspecting traffic. For instance, traditional signature-based malicious traffic detection, such as Zeek and Snort, relies on deep packet inspection (DPI) to check if the packet payloads contain abnormal data. For instance, malware, binary files of malware. However, attackers can encrypt packet payloads to invalidate DPI because DPI cannot inspect encrypted data unless it can decrypt the traffic. So it's impossible for existing traditional signature-based method to detect encrypted malicious traffic. In recent years, machine learning-based methods are designed to detect sophisticated attacks. Different from signature-based detection, machine learning-based detection does not inspect packet payloads. Instead, it extracts the features of traffic. For example, the number of packets in a flow and the flow compilation time. After that, it puts the extracted features into machine learning models to classify the flows into benign flows or malicious flows. Powered by machine learning, these methods can detect many advanced attacks and even unknown attacks. However, our empirical studies show that the existing machine learning-based detection is unable to detect so many encrypted attacks. But why? Because the feature of encrypted malicious traffic are similar to that of benign traffic. Here is an example. The patterns of benign mail traffic and malicious spam mail traffic are very similar. Spam flows may deliver arbitrary sizes and types of contents to mimic benign users. So it's hard for existing machine learning-based detection to differentiate benign and malicious mail flows according to the traffic features. And similarly, many encrypted malicious flow, other than spam flow, also exhibit benign flow features. So the existing machine learning-based methods are unable to detect so many attacks. The observation that motivates this research is the abnormal interaction patterns among attackers and victims. Back to the previous example, although we cannot detect malicious flows according to the traffic features of a single flow, however, the flow interactions between the spam bots and SMTP servers are significantly different from the legitimate communications. Even if each single flow of the attack is similar to benign flows, more precisely, to make spam more profitable, the bots have to frequently interact with mail servers for mail flooding. Based on this observation, in this work, we set out to explore utilizing the interaction patterns among flows for malicious traffic detection. For this purpose, we designed the flow interaction graph It represents interaction patterns as graph structural features. On the graph, vertices denote IP addresses and edges denote flows. We apply unsupervised graph learning to detect various attacks, and especially encrypted malicious traffic. Our method does not require any prior knowledge. For example, labeled training sets for unknown attack detection. Okay, moving on, I will present the high-level architecture of our solution. Our graph-based traffic detection system consists of 3 modules. The first one is graph construction module. The detection system monitors ongoing traffic, which contains both benign and malicious flows. First, the system raises each packet to extract basic properties, for instance, protocol, length, and packet arrival interval. Next, the module constructs flows by grouping the packets with same tuples of protocol, source and destination addresses, and ports. At the same time, we classify the constructed flows into long flows and short flows according to a predefined threshold. Next, we construct edges denoting short and long flows separately. We identify similar short flows, for example, massive SMB echo reply flows, and the volumes of DNS flows, and as mentioned, spam flows. And as for long flows, which compare small packets, we extract fine-grained features vector to describe their complex patterns and use one edge to represent one long flow. Finally, we mix all the edges and vertices as the graph, named the flow interaction graph. In the next 2 modules, we will apply graph learning to identify abnormal edges, which denotes attack flows. The second module is graph preprocessing module. First, we split graph by extracting strongly connected components. At the same time, we extract the cross-grained statistical features for each component. After that, we cluster the features to identify components with abnormal features. Next, for each identified abnormal components, we cluster the edges to merge duplicated edges, indicated by the green circle on this slide, which will significantly reduce the processing overhead of graph learning. The last module is graph detection module. First, we identify the critical vertex, which connects many edges. In specific, we identify such vertices with high degrees by solving an edge covering puzzle. Next, for each critical vertex, we cluster the connected edges according to both flow level features and graph features, and outliers are the edges denoting malicious flows, malicious traffic, and the source and destination of the edge denotes attackers and victims. Finally, the system extracts subgraphs as the indicators of attacks, notify operators to instantly respond to detected attacks. Here is the high-level design of our system. Now let's dive into some design details. A challenge lying in the efficient graph construction is how to reduce the density of graph. It's clear that the number of ongoing flows and IP addresses are prohibitively high for graph building. Empirical studies show that there are over 50,000 active addresses in the AS which generate over 3 million flows per hour. And as shown on this figure, using one edge to denote one flow will construct a very dense graph. Apparently, it is impossible to learn such a dense graph, so we cannot use one vertex to denote one address. This issue is like the dependency explosion problem in provenance graph analysis. Okay, so what is the best way? We observe the short flows and long flows exhibit distinct distributions. That is, most flows are short flows, but most packets are in long flows. So it motivates us to build edges for short and long flows separately. We find many short flows are surprisingly similar, so we can use one edge to denote thousands of similar flows. And for long flows, to retain the complex patterns of the flows, we extract the distribution features. In summary, one edge on the graph may represent one long flow or many short flows. One vertex may represent a group of addresses or a single address. The following figure compares the graphs before and after reduction, where our method reduced over 94% edges and 90% vertices. The diameter indicates the number of addresses noted by the vertices, and the green edge denotes a vulnerability scanning from Manila, Philippines. Another challenge is how to realize efficient and fast graph learning. Now, the graph is still very large. Our solution is excluding benign components. More details can be found in our paper. We validate our method both theoretically and experimentally. First, we proved the effectiveness of our graph-based detection by developing an information theory-based analysis framework. We modeled flows as discrete Markov chain. By comparing the entropy of the chain and the entropy of the graph, we proved that the information preserved by the graph is near optimal, and the margin to the optimal value is even negligible as shown on this figure. Finally, we implemented our system by using Intel data plan development toolkit for high-performance packet processing. We established a physical testbed where 92 different attacks were replayed, and 48 of the attacks were constructed by encrypted malicious traffic, including encrypted flooding traffic, for example, troll-spam attack, and the encrypted web attack, for example, Nginx injection, and malware-generated traffic, including command and control channel traffic, and malware delivery and update traffic. Now, let's move to the results. First, we show that our method outperformed the state-of-the-art methods by large margins. Over half of attacks with encrypted traffic cannot be accurately identified by all the baselines. Second, we observed our method can identify many sophisticated attacks. The following figures are subgraph that contain identified malicious traffic. The first graph shows troll-spam attack. The outer layer denotes the destination of the flooding traffic, and the inner layer denotes botnets. The second graph illustrates a password cracking attack, where an attacker attempts cracking servers that reside in different subnets. The third one shows an attack targeting a website, and the last one shows a P2P malware campaign. Finally, we measured the efficiency of the development method. The results show that it realizes high analysis throughput, 121 gigabits per second, with very low detection latency. In conclusion, we developed an encrypted malicious traffic detection system that is built upon the flow interaction graph, which represents interaction patterns as graph structural features. From this work, we observed many kinds of attack traffic exhibit benign flow features, which implies it's no longer possible for many existing methods to detect many attacks, both signature-based methods and machine learning-based methods. So we need to design new features to tackle this issue. For example, graph feature used in this paper. And finally, the idea of graph-based traffic detection is derived from provenance graph analysis, which is used to detect advanced persistent threat, APT, topic of the second paper in this session. And we believe in the future, the flow interaction graph can be applied to many other network applications other than the traffic detection in this paper. For example, network telemetry, management and measurement, audit, and diagnosis. That's all. Thank you.
Hello, my name is Jacob from KDH in Sweden. One thing that came up earlier in this session was with the provenance graph was that if the attacker has the ability to inject a lot of benign traffic in between its malicious activity, then that introduces a lot of new edges in the graph. Would this method be resistant to that type of behavior?
Okay, I see. It is a very good question. We evaluate this point in our paper in the appendix. You mentioned an attacker may inject benign flows along with the malicious flows to create many edges to mimic benign users. But however, it increased the frequency of the interaction, and thus it can be captured by our graph learning. We believe it's more it's hard to manipulate the interaction patterns of the attack because it may have impacts on the efficiency of attacks. Can you understand?
Thank you.
Thanks for this question.
Actually, I have a quick question. If you look at it from the very high level, look at the network flow information means you need to ignore the payload. From the very high level, that is there's a lot of missing information. Will that be under that view, what do you think is the main limitation of this approach?
Okay, I see. I think the limitation of this work is that what you mentioned. It cannot inspect the payloads, but however, payloads provide many important information. We observe many existing attacks, many prevailing malwares are still use plain text channel to exchange their information. For example, malware binary. We can see the malware binary directed from unencrypted traffic. So I think it is the biggest limitation of our method. Just as you mentioned, it cannot inspect the payload of traffic, but actually the payload contains many important information.